So in this video, we continue the study of buffers, and this time we not only look at whether we can identify whether something is a buffer or not, but calculating the pH of this buffer solution. So let's jump right in, and let's say that we have a buffer solution that is of a weak acid. We'll just call it HA as a general name for the weak acid, and it's 0.05 molar. And we have a salt called Ka, which of course has its conjugate base of the weak acid included in it. I put potassium in there because remember potassium salts are always soluble. And this is of 0.1 molar. And I also know that the equilibrium constant for this weak acid is 1.0 times 10 to the negative fifth. I should probably put this to at least 2 sig figs. It'd probably be to 3 if I looked it up in Appendix D. So step number 1 when you're solving these problems is to ice the weak acid or base with water. And so we'll make an ice table of HA reacting with water, and then we get some H3O plus and some A minus. And then we'll write ICE down right below it. And the concentration of the weak acid is 0.05 molar right up here. Water is pure liquid, so it doesn't matter. The H3O plus ion concentration, there's none there to start with. And the A minus ion concentration comes from the Ka because it dissociates and it gives you 0.1 molar right here. And so you can see we have a common ion effect type problem. And so we have a change where we lose X, gain X, gain X. We have 0.05 minus X, X, and 0.1 plus X. And now we can do some magic by ignoring these X's and saying they're small. And then we can set it to the Ka expression, which would be products divided by reactants to the power of the coefficients, and ignore the water because water, of course, it does not affect the equilibrium because it's a pure liquid. And so now we put in the letters, and so we have X times 0.0 A minus 0.1. This should be 0.1 right here. And then this should be 0.05. So 0.05 should go on the bottom right here. So 0.10 coming from right here and 0.05 going right here. And then this is set equal to the Ka, which is 1.0 times 10 to the negative fifth, which is the Ka right here. Okay, and if I do this and I solve for X right here, I would take 1 times 10 to the negative fifth, multiply it by 0.05, bringing this over here, and then dividing by 0.1, and I would end up with 5 times 10 to the negative sixth. And so my H3O plus ion concentration would be equal to 5 times 10 to the negative sixth. And then to find the pH of this, of course, I'd do the negative log of the 5 times 10 to the negative sixth, negative log, second answer, and I get a pH approximately equal to 5.3. So calculating the pH of buffer systems is very similar to calculating the pH of a common ion effect problem. But there's an easier way as well. If you're a good recognizer of these buffer systems, you can actually take this equation right here and manipulate it just to find the pH. So watch this. And you guys that like math will fall in love with this kind of stuff, and you guys that don't love math so much, that's okay. You can just watch and follow along, and who knows, maybe it'll make you like it a little bit more. So here was the equilibrium constant expression we had. We had Ka equaling H3O plus times the A minus divided by the HA right here. And my goal was to find this H3O plus. And so I'm going to solve this by bringing HA on this side and A minus on this side. So H3O plus now then is equal to Ka times the HA divided by the A minus. And then I'm going to take the negative log of both sides. So when I take the negative log of this side and the negative log of this side, I end up with the negative log of H3O plus on this side and the negative log of this entire quantity over here on this side. Now, this negative log of H3O plus has a new name. It's also known as the pH. And so I can substitute pH in for this. And so therefore pH is equal to the negative log of this thing. When you have the log of something multiplied by something else, remember the rule of logs actually lets you, I'll use the word distribute or push the log times Ka plus this logarithm. And so I'll rewrite it this way. The negative log of Ka plus the negative log of the HA over A minus. This negative log of Ka actually has a new name. It's also known as the pKa. And so now my equation has become pH equals pKa plus the log of HA over A minus. And now, according to the rule of logarithms, I can take this negative log right here and rewrite it when I have two things divided and I'm not logging them as the top minus the bottom logarithm. And so I'm going to leave the negative sign out here and I'll write log of HA minus the log of A minus right here. Then I'm going to distribute this negative sign in here and this negative sign in here. And then I have the pH is equal to pKa plus the log of A minus minus the log of HA. Rewriting this one more time, remember when you subtract two things that are logs, you can actually have this species divided by this species. And so my final equation ends up being pH is equal to pKa plus the log of base over acid. This equation is super popular in acid-base buffer chemistry, and this equation is called the Henderson-Hasselbalch Equation. It's used as a quick find for the pH of a buffer solution. And so this equation you should highlight, circle, square, star, or box, and then let's do one example problem of it. Here's the way to write it in general. pH is equal to pKa plus the log of base over acid. So let's calculate the pH of a buffer who's 0.1 molar in HC2H3O2 and it is 0.1 molar in NaC2H3O2. And so right away from last video you recognize this is a weak acid and its conjugate base with a soluble cation on the front. And then I know the Ka of acetic acid by looking it up in Appendix D is 1.8 times 10 to the negative fifth. When I recognize it's a buffer and it's asking me for the pH, I can go directly to this equation. I can find the pKa by taking the negative log of 1.8 times 10 to the negative fifth. And then I can take the logarithm of the base over the acid. And in this case, my base is the anion right here, which is 0.1 molar. And, oh, it turns out the acid has the same concentration, 0.1 molar. Math people are jumping up and down right now because 0.1 divided by 0.1 is 1, and the log of 1 is 0. And so then the pH is actually just the negative log of 1.8 times 10 to the negative fifth, which turns out to be 4.74. So the Henderson-Hasselbalch equation is also really helpful in determining ratios of acid, weak acid to conjugate base amounts to help make buffer solutions. And so here's my last sample problem during this video. This one says, calculate the ratio of equilibrium concentrations of the weak base right here and its acid if the buffer has a solution pH of 3.98 and its Ka is 1.8 times 10 to the negative fifth, which we saw over here already. So now the thing that I know is the pH right here. The pKa I can find by taking the negative log of this. And what I want to know is the ratio of this base right here to this acid's concentration. And so this is the piece that I want to know right here. I can find the pKa by taking the negative log of this, and then the pH, of course, is 3.98. So my equation becomes 3.98 is equal to 4.74, because that's what the negative log of 1.8 times 10 to the negative fifth is, plus the log of x. I'll call this ratio of base to acid x. So bringing 4.74 over to the other side, the log of x is equal to negative 0.76. And if you forgot to do how to do this on your calculator, to undo this logarithm, I would use the 10 to the x key. Whoops, excuse me, 10 to the x key, so 10 with a little caret, and then I'd put in the negative 0.76, and I should end up with 0.174. That's my ratio of base to acid concentration. So in this video, you should have learned two major pieces. Number one, should have recognized that we can calculate the pH of a buffer system by doing a common ion type problem with ice tables. And then number two, should have recognized that there's a quick way to find the pH of a buffer solution or a buffer system. And as long as you're good at recognizing the buffer system, you can use the Henderson-Hasselbalch equation, which is pH is equal to pKa plus the logarithm of the base over the acid concentrations.